Hello class, today we're going to be continuing on with this unit. We talked about lookup tables last time, and we're going to talk about this extension of it called a hash table. Now, if you remember, there was a limitation with lookup tables. Now, a very good example was, zip codes. I could look up the city of a particular zip code, but there's a lot of zip codes that are empty. There is no city for zip code 0. There is no city for zip code 600. So we end up with this lookup table that's, very empty. And if you have a lookup table that's 90% empty, you're wasting a lot of space, and you don't want to be doing that. So what can we do there? Another issue could be this. Maybe the thing that you're looking up is not a number. If we want to look up a zip code is a number, so that works well in an array as an array index. But what if I want to look up a city? I want to find the zip code of a city, so I kind of want to reverse this. How would I look up the zip code of Barre, Massachusetts? A string is not a number, so how then would I be able to use that as an index into a lookup table? So that's kind of another problem with the lookup table as we have it here. So what can we do? What we do is create what's called a hash table. Now, a hash table starts with a lookup table. It starts with an array. So maybe I have an array from 0 to, say, 999. And it's filled with information. Let's actually just use zip codes just as an example. So maybe I have San Jose, and the zip code there. I'll just make something up, actually. And then maybe I have another city, Sacramento. And I know there's lots of zip codes in Sacramento, but I'll just, for this example, just use this particular zip code there. So I need some way to turn the string into an index value of an array. And so we create something called a hash function, which takes in the key, in this case the city name, and turns it into some number from 0 to 999, so that we can then say, okay, where is San Jose? San Jose is right here. Where is Sacramento? Oh, Sacramento's right here, 623. And so this function here, this hash function, generates an array index for us. And so then we could actually kind of optimize things so that even though we might have a wide range of these things here, it will always map to a number from 0 to 999. So if I had 100,000 zip codes here, and I send it into a hash function, maybe I can just have, instead of 100,000 different zip codes mapped to 100,000 different array elements, maybe I could squeeze it into, 40,000 cities, because I really only have 40,000 cities. Something like that. So we have ways to then optimize that, and we also have ways to turn non-numerical keys into numbers. Okay, so that's the idea of a hash table. Now, with that hash function can end up mapping different keys to the same array index. And in that case, we have what's called a collision, and we'll talk about how we deal with that situation. Now, to make a good hash function, you would prefer, or you want, your keys to be mapped uniformly to the indexes. So you kind of want it to be random, but it's not random. It doesn't, where it goes. San Jose will always be mapped to the number 23. Sacramento will always be mapped to, say, the number 526. But what happens is it's uniformly mapped, so you don't end up with 10 cities all mapping to the same number all the time. You'd really want it to be kind of uniformly distributed across all the different array indexes that you have available. Again, that's done to minimize the number of collisions where multiple things map to the same index. But inevitably, you will have collisions in your hash code. And so we have to have ways to deal with those collisions. And we have two ways. One way is called probing, and the other way is called chaining. Probing is the idea of this. Suppose I have some key that I'm looking up. My hash function generates the value 126. So I go to 126 and I say, does that entry peach, is it in that array entry index value? No, it's not. So then I will create a probing function that recalculates the index. So in this case, we're going to do a +2 function, a very simple probing function, +2. So 126 plus 2, is it peach? No, it's not. Add another 2. Yes, we found it. So it's right there. Okay, so this is the idea of probing, to look for an empty spot where we could stick the value in if it's not there yet, or we can keep on searching with this probing function to find where that key happened to be stored. Another way is chaining. Chaining's actually the way Java does it. Chaining is this idea that it's kind of like every array holds a binary search tree itself, or a bucket of stuff. So we could actually put multiple things inside each entry. So peach maps to 126, and we stick it there inside of a bucket or a binary search tree or whatever we want. It could be a simple linked list if we want it to be. A BST might be better just because it's a little more efficient than a linked list, but you know, linked lists aren't terrible either. And so in this way, you don't really have to do probing. You know it will be at location 126, but you might need to do a little searching within this data structure or with this bucket here to actually find the word that you're looking for. Okay? Now, Java has this collection thing called the hash set and the hash map, and both of these implement this idea of a lookup table that has a hash function that allows us to look up a certain key value. So a hash map is kind of like a dictionary in Python. It converts a key into a value. It maps something. It maps your input into an output. My zip code into a city, or maybe my city into a zip code, or whatever. Hash set, it's just it's like sets that we've seen, tree sets, where we can just put a bunch of stuff into it, and then we could just find out, is this element in the set already or not? Now you might wonder, how is it different than a tree set or a tree map? Tree sets and tree maps will use a binary tree, a binary search tree. Hash sets, hash maps, they use hash tables. So how is it better or worse? The hash table, hash maps, probably in general are slightly more efficient, but with hash trees, or sorry, tree sets, tree maps, you also could get out of it some ordering, because a binary search tree is also ordered. And so if you wanted to iterate through the items in a tree set, you could actually do it in a nice sorted, ordered way. Whereas in a hash set, hash tables don't have any sort of sorting. You know, it's just all over the place in terms of where things are. And so there is no notion of sorting. There's no notion of ordering in a hash table. Now, we talked about how collisions will inevitably happen. And ideally, you want to minimize the number of collisions, actually. We don't want to have to resort to, you know, chaining a lot or probing a lot. We would like to look into that index and get the information right away, instead of going into that index and then continuing to search down, into that big search tree a lot. So the way we kind of we have metrics to kind of measure that, and the metric is called a load factor. Basically, it says this: the load factor, the current load factor, is how many items do we have divided by how many buckets there are. So say you have an array of 100 buckets and you stuck in there 500 items. Then you have a load factor of 5, and that's actually very high. I'll talk about what Java kind of tries to achieve in a second. Now, with the hash set or hash map, you can set what's called a load factor limit. And what we mean by that is that's the maximum number of items divided by the number of buckets. And it's a limit, which is saying I don't want the load factor to ever become bigger than this amount. So, for example, Java actually sets up a load factor limit of 75%. So if I have 100 buckets, the maximum number of items that I could put into that hash table is only 75. And then what Java will do is, if you try to put in a 76 element, it's going to grow the array to a bigger size. It'll double the array from a size 100 to 200, so that load factor, the load factor will always be under this limit that you set up into your hash table. So I'm going to use the word load factor, which is the current load factor of your hash table, versus load factor limit, which says what is the capacity, in a sense, of my hash table. What's the maximum load factor I will allow before I grow my array, my lookup table, to a bigger size. And I used the word capacity, in analogy to the array list, because an array list has a certain initial capacity, and once the size of that array list exceeds the capacity, then we boost up the array list to a bigger capacity. In the same way, we boost up the array size if our load factor ever gets bigger than the load factor limit. Now, we want to make sure that the load factor isn't too big or too small. If the load factor is too large, we get lots of collisions. So if our load factor is 5, that means every time we're going to have to continue searching to actually find the element. If the load factor is too small, that means we're wasting a lot of memory. We have a huge lookup table, but we only have a handful of elements actually stored inside the hash table. So again, what Java does is it defaults by setting up the load factor limit to 75%. And what it does again is whenever the load factor exceeds that limit, it'll enlarge the array table. Now, ideally, you don't want to do that too often. Just like array list, you want to kind of estimate the size that you need, so that you're not spending time growing the hash table every single time you add elements into the hash table. So, when you create new classes, you need to have some sort of hash function, right? Hash function is a very key thing. And so in Java, there's this method called hash code. And this is kind of the hash function that generates that special number. Now, it's not exactly the fullness of the hash function. The hash code itself returns any sort of integer within the entire integer range. And then Java will take that number, that integer number, and then it will further map it into the legal range according to how big your array is. So this hash function is kind of broken into two steps. We have the hash code method that generates kind of a very uniform integer of the entire range from negative, maybe 2 billion to positive 2 billion or whatever that is. And then there's another stage that takes that huge integer and maps it down to a limited range of integers from 0 to, the size minus 1 of your array table. Okay? Now, for a string, for example, this is the hash code function. And it's designed to be something that, again, is uniform. And also, the other requirement of a hash function is it should be fast. It should be something that you could generate very quickly, because you don't want this hash function to be like an O(n) activity that depends on, or O(n) squared activity that just takes a very long time. Okay? So, for example, this is the string hash code. And then you could create your own personal hash code. Suppose your person class that you're creating has a first name, last name. We want to create our own hash code for that, and we can construct that by saying the first name hash code plus the last name hash code becomes the person's hash code. And a lot of times what you can do is you can combine different hash codes of the fields of the object that the class that you're making to create your own personalized hash code. Now, it's important that when you generate the hash code that you you make sure that it's consistent with the compare to. So if x is equal to y, where x compares to y is 0, you should make sure that your hash code is also generating the same hash code for the x and for the y. They should always be in agreement with each other. So this is just a summary of some of the hash set constructors. If you don't give it any sort of input, it'll generate a table of an initial capacity of 16 and a load factor limit of 75%. You can also make a hash set that has a larger capacity. You can make a hash set that has an initial capacity as well as some other load factor that you're okay with. And you could also feed the hash set with any sort of initial collection, and it'll then turn that collection into a hash set. Hash maps, same idea. You can have 3 different kinds of constructors to initialize your hash map. Okay, just as a review, I'm gonna, you read the question, I'll pause it, and then you can think of it in your head before I reveal the answer. What is the main difference between a lookup table and a hash table? What is a collision? What are 2 common techniques for resolving collisions? And Java, by the way, uses chaining. What is a bucket? What is a load factor? How is a hash table performance affected when the load factor is too high or too low? What happens to a hash set or a hash map when the load factor exceeds the limit that had been set? Hash sets no-arg constructor sets the initial capacity to 16 and 75%. How many items can be stored in this table before it is rehashed? So 16 times 75%. What is the sequence of values returned by an iterator for a hash set? What is the range of values for the hash code method? Which methods of an object are used to find it in a tree set or a hash set? Okay, That's the lesson for today, class. Have a good day, everybody.